So we are happy to have Pratik Rath from University of California, Berkeley. We'll be talking about quantum gravity, modern approaches to an age-old problem. Pratik, you can start.
Thank you so much for the invitation to give a talk here. What I'd like to do today is try to give you a sort of broad strokes overview of the kind of work I've been doing, and in particular, some modern approaches to this problem of quantum gravity. So let me first set the stage by talking about the problem of quantum gravity itself. Mostly all of you know that this is like a fundamental problem in theoretical physics, which involves trying to unify the two main paradigms of our understanding of nature at this point. There's general relativity, which describes the classical physics of large-scale objects in our universe. And this has been a tremendously successful theory. Of course, recent successes of it include imaging a black hole using the Event Horizon Telescope and finding gravitational waves from black hole mergers. There's, of course, also quantum mechanics, and in particular quantum field theory, which has been the leading paradigm for understanding the quantum physics of nature, especially at short scales. And this has been tremendously useful both in particle physics, where represented here by the discovery of the Higgs boson, and also in condensed matter physics, where it's helped us understand exotic phases of matter like superconductors. So the idea, of course, is clear. We want to find some common theory which is unified, and it has these two paradigms as limits of it. But of course, it's a difficult problem, right? So this is a fundamental problem, but it's been difficult. It's been an age-old problem for a good reason, because we've made very slow progress on this problem. Now, traditionally, there were a lot of attempts which were more top-down in the sense of, for example, string theory, loop quantum gravity, or any other approaches that people have tried, where we start by positing some theory and then try to find general relativity and quantum field theory in various limits of it. But the difficulty is, of course, trying to make a connection with physics in that we have access to. And so my approach, and in recent years, a lot of the people here have tried this approach, which is to just start with what we understand about nature, which is these two paradigms, and then try to sort of flip the arrows and go from a bottom-up perspective, where we try to use what we understand about nature and use some basic axioms about what we expect for this complete theory, and try to build upwards starting from this. So it's a more bottom-up sort of approach. Now, how do we go about doing something like that? Well, there's a few things that sort of guide us in this pursuit. And the key thing is basically black holes. And in particular, black hole thermodynamics and the black hole entropy formula in particular. So this is this beautiful formula that tells us that a black hole essentially behaves like a quantum system with this many number of degrees of freedom, which is measured by its area in these appropriate units. And this is a very interesting formula in physics, of course, because it involves all of these various aspects of physics from a low energy perspective, which seem very different. Boltzmann's constant for thermodynamics, speed of light, which is relativity, h bar, which signifies quantum mechanics, and g, Newton's constant, of course, signifying gravity. So a complete understanding of this formula presumably involves us having a unified understanding of all of physics as we understand it today. The history of physics, of course, tells us once we have an entropy-like thing, we should have some sort of statistical mechanical explanation of it. And that's sort of one thing that has been the holy grail of quantum gravity. We're trying to understand that, and that would hopefully lead us to some sort of a unified picture for how quantum gravity works. Now, this formula was initially derived by just staring at Einstein's equations and looking at perturbations of black holes and rewriting the Einstein equations in a form where it resembles the laws of thermodynamics. But there's also another approach which was pioneered by Gibbons and Hawking in the 80s, which is that of the gravitational path integral. So I'd just like to briefly mention that because it's going to play an important role in the rest of what I'm going to say. This was an approach that was people were very interested in the 80s and so on, where you try to mock up something like the quantum field theory path integral, where in gravity we expect that we fix boundary conditions at infinity. So here you fix some thermal boundary conditions with some boundary circle of length beta. And then you integrate over all possible geometries that are consistent with that particular boundary condition, weighted by the Einstein action, just like you would in the Feynman path integral of quantum mechanics. When you do that, there's a semi-classical approximation where you pick up a saddle point, which is basically a Euclidean version of the black hole. And by computing the action and the appropriate derivatives, you find this precise Bekenstein-Hawking formula. So there's different approaches to getting at this formula, and the gravitational path integral approach will play a more important role in what I'm going to say. So an interesting part about this formula, of course, is the fact that the entropy goes like the area and not the volume. And so it inspires this idea of holography, or what's also been recently called the central dogma, which is that as seen from outside, a black hole essentially looks like it's built out of this many number of degrees of freedom, which heuristically sort of tile the horizon of the black hole. So here it's represented in this picture by bits, which are Planck-sized areas of the horizon, and that gives you some number of degrees of freedom, which should be sufficient to describe everything inside the black hole. So this was sort of some inspiration that people drew from this sort of a formula. But of course, string theory then gave us a more concrete version of this idea of holography. So there is what hopefully all of you are familiar with, which is the ADS-CFT duality, which is a duality between gravitational physics in a universe which has a negative cosmological constant, which doesn't seem to be the same as what we have in our universe, but nevertheless, it's some setting where we understand the gravitational physics as being related to the non-gravitational physics of a conformal field theory that lives on the boundary of this cylinder. And the duality initially basically told us that all of this gravitational physics is related to the non-gravitational physics in the CFT, but we've tried to understand in a deeper way how this duality works in recent years, and ideas from quantum information theory have played an important role in trying to do this. In particular, one of the ideas that has been a hallmark is the Ryu-Takayanagi formula. So the Ryu-Takayanagi formula is a formula which resembles a lot the black hole formula, where I've set all the other constants to 1, just keeping the dependence on Newton's constant. So it looks a lot like the black hole formula, except it's in a much more general setting. And what it says is, in this CFT that's dual to ADS, we can try to compute the entanglement entropy of a region of the CFT, which is labeled here by capital R. And the entanglement entropy of this region is given by an area, a Bekenstein-Hawking-like formula, which is the A over 4G of a particular surface. This surface labeled gamma R is the minimal surface, the minimal extremal surface that's homologous to the boundary of R. So here in the figure, you can see there's this surface, which is the minimal surface hugging the boundaries of R. And it encloses this green shaded region, which is called the entanglement wedge of region capital R. And these ideas, which often are put under the slogan of what's called it from qubit, have led us to go from the Ryu-Takayanagi formula to understanding that there's a sense of subregion duality in this ADS-CFT dictionary, where the region capital R on the boundary is able to extract all of the bulk gravitational physics in the region little r, which is the shaded green region, And it's also something that's been termed entanglement wedge reconstruction. So given access to some particular region, there's some part of the bulk that we can understand using just that region and having access to no other part of the CFT. So obviously, initially we started with a more coarse dictionary where it said ADS equals CFT, but now we understand this part of the CFT is dual to this part of ADS in a more refined way. Okay. So a concrete toy model which has helped us in this process of understanding this holographic dictionary is what's called the random tensor network. So this was introduced in this 2016 paper by Hayden and others. And the way it works is we have a tensor network. So a tensor network is basically we have some sort of discretized version of hyperbolic space. It need not be hyperbolic space, but here I'm just drawing that as an example. And we have a graph which has vertices and edges. At the vertices, one picks random tensors with the appropriate number of legs, and then contracts them together according to the edges of the graph. So here, all the blue tensors are some random tensor with 3 legs each, and then they've been appropriately contracted with their neighboring vertices. And in the limit where we take these random tensors to have a large bond dimension, which is basically related to the semi-classical limit of ADS-CFT, one finds essentially that this works basically like ADS-CFT. In particular, it has a Ryutakinagi formula, which says that the entanglement entropy of a boundary region, capital R, is given by a minimal cut through the graph. There's also a version of entanglement wedge reconstruction, which says that if you have access to capital R, you can act with operators that act on the bulk region, which is the green shaded region, which is the entanglement wedge. So the idea here is that this is something which is a simple toy model where we have a lot of control and we understand how this dictionary is working. In the context of ADS-CFT, we have nowhere near as much control. But the idea is that somehow the holographic dictionary works in analogy in a similar way. So in particular, this tensor network is both, it's simultaneously a preparation of the boundary state. So this tensor network, after you've done all the contractions, has some open legs that are living on the boundary, which where we have a state that we can interpret as the CFT state. But also it has a geometry. The tensor network has some graph structure, which you can think of as a discretized version of the bulk geometry. So
Sorry, but in what sense is gravity here in this
yeah.
in the book?
Good. That's a good question. This is a very toy version of it. So here, gravity is just it's there in a few senses. I will say a little bit more about this later, but for now, I can just say that it's capturing the geometry. So in a kinematic sense, there is gravity in the sense of just like the fact that space-time is like the curvature of space-time gives you gravity. But also there's a sense in which the calculation of, say, the entropies and other quantities involves, there's a very sharp analogy between the calculation of these quantities in the random tensor network and in gravity, which basically involves this gravitational path integral. And I'll say a little bit more about how that works. But there's a one-to-one correspondence between configurations that show up in the random tensor network calculation and configurations which show up in the gravitational path integral calculation.
Pratik,
Yes.
what is the thing that corresponds to diffeomorphism?
Yes, that is actually one of the main questions that is missing in this understanding of tensor networks. In particular, one of the things that I will try to emphasize later is that these ideas suffer a little bit in situations where there's time dependence, and it usually works best when the ones we understand best is when it's on a time symmetric slice or when there's time independence, and that is essentially because it's sort of missing what you said. Like it's missing the Hamiltonian constraint. It's missing gravity in the sense that also Sujay was asking about. So what it's the idea here is not that the tensor network is ADS-CFT. It's more that there's a sense in which it reproduces aspects of ADS-CFT or gravitational theories, and that we can learn something from this simple model, which we can apply to gravity when it can teach us something about gravity. So it doesn't have diffeomorphism invariance in that sense.
And just one more question
Yeah.
regarding the same question, that should we think of it as a generalized free field theory? I mean, when we study ADS-CFT for the first time, we just start with the bulk and study generalized free field, not
Yes.
because the bulk is not dynamical in a sense.
Yes. It might, like the generalized free field does know a little bit more than the tensor network knows. So let me say the sense in which this is ADS-CFT, which is that imagine you had n equals 4 super Yang-Mills, right? Like, so this is some particular CFT where you can try to look for the ground state. That ground state, you're basically, this is a standard thing that's been used in condensed matter and quantum information, which is you can use these tensor networks as a variational ansatz to look for the ground state of some theory like that. That tensor network, which constructs the ground state of n equals 4 super Yang-Mills, will essentially look, since it's a very chaotic theory, will essentially look like this random tensor network, and a lot of the features of the random tensor network will be true for the tensor network that constructs the specific ground state of n equals 4. Now, if you really construct the ground state of n equals 4, then you can compute all sorts of things, right? So you can use it to compute whatever dynamics you like and so on. Here, what we're doing is sort of modeling that. Of course, compute the ground state of n equals 4 is a very complicated thing, and we don't really have access to that. But we're just modeling that by this random tensor network, hoping that it still reproduces some aspects of it. So generalized free field would be a part of that if you really had this true ground state. But if I just think about it at this coarse level of just having this random tensor network, then in some sense the generalized free field sometimes knows a little bit more than what the tensor network knows, just because it knows about, say, dynamics in time and things like that. So they're sort of little complementary. They know different aspects of ADS-CFT.
Okay, thanks.
Yeah. Sorry, just one thing. The link, is that encoding the entanglement, or is that not the case? Like the link between
the edges? You mean the edges? Yeah. So the edges you can think of as, before we formed the edges, there's just at a tensor there's 3 of these like links coming out, and the way it's paired is by projecting onto maximally entangled legs. So it's precisely entanglement that's building up that edge.
Okay. And if I understood correctly, this network fills up the bulk, does it?
Yes.
And for the same capital R, I could consider many smaller regions. So
Yes.
they're all equivalent, they all.
So little r is defined by, first, given a capital R, you look for the minimal cut through the graph. So that picks out a particular gamma r, and then everything that's bounded inside that picks out a little r. So that's actually a feature also of ADS-CFT, where in principle you could have imagined many area of which surface, right? It could be any surface, and this Ryu-Takenagi formula precisely tells you which surface it is, and the random tensor network matches exactly that.
And what is the minimal cut? What is
the minimal cut is basically like you're trying to cut the minimal number of bonds, the minimal number of links.
Okay, all right. Thank you.
Which is separate, yeah.
Pratik, you mentioned about this ground state of ADS-CFT, but you are working in a strongly coupled system, infinite coupling, right?
Yes.
So what are the ground states here in this?
So as I was saying, what I was trying to say was that in principle, in this strongly coupled theory, you could like numerically try to find what this ground state is using this as an ansatz. In practice, what we're doing here is not that, because that's quite a hard thing to do, as you said. What we're really doing is using this random tensor network as sort of a model for that. So, so this is like maybe a familiar version of this is like when people use the eigenstate thermalization hypothesis, right? So in the ETH, what people say is for a generically chaotic enough theory, the matrix elements of simple operators in high energy eigenstates look random. What that really means is you may be interested in one particular theory, and in that particular theory, these will be some very specific numbers. But if you squint enough, like if you just replace that with a random matrix, it sort of does the job approximately. It's in that sense that the random tensor network is being used here. So if we want it to mock up the ground state of, say, n equals 4 super Yang-Mills, but of course we don't have calculational control. But nevertheless, if we just treat these tensors as random, it still reproduces some of the features of it.
But in finite temperatures, the random matrix theory only gives you the diagonal part of in the ETH sense. If you calculate the operator expectation value, you get the diagonal part correctly with the random matrix theory. However, the off-diagonal fluctuations are very large when you have finite temperatures.
I mean, usually they're
In a
exponentially
realistic
suppressed.
system, yeah.
I mean, usually they're exponentially suppressed, right?
Yeah, but there's also another function which is sitting in front of that exponential term. And that may be crucial for realistic systems.
I mean, what I was trying to emphasize was that, I mean, like in some generic CFT that you like, I mean, if you wanted to compute the expectation of some simple observable in some high energy eigenstate, it's like up to exponentially small corrections given by the thermal answer, right?
Yeah, that's true. But yeah, here it is strongly coupled system as well as there's a finite temperature. So I'm not sure whether all of these.
So right now, what I'm drawing is just for the ground state. That won't play an important role. Like this is, you can imagine this is at zero temperature. But even if you have finite temperature, the bulk dual is slightly different. It'll have a black hole in the bulk instead of having just this hyperbolic space. But nevertheless, even in a theory like n equals 4 at strong coupling, the ETH is still kind of true. It still doesn't matter like up to exponentially small corrections that
Has it been demonstrated the ETH?
It hasn't, but a lot of calculations that have been done are consistent with it. So, I mean, proving the ETH is of course really hard, but it's been tested for like, some correlation functions can be computed, like both using the bulk as well as using the boundary. Especially in lower dimensional CFTs like 2D CFT, we have a lot more control over these calculations, and people have demonstrated how the ETH really holds and what the bulk dual of that is.
Okay, yeah, thanks.
Thank you. Okay, so the idea here is that, yeah, this is some sort of toy model for how the holographic dictionary is working. Okay, so that brings me to my research themes and what the sort of work I've been doing. And as I've emphasized already, one of the key things is trying to use this lens of quantum information to try to understand quantum gravity. And there's many different ways in which this has been applied. Entanglement measures have played an important role in trying to understand this holographic dictionary. Ideas from quantum chaos and random matrix theory have played an important role in recent years, as well as complexity theory. Now, you'll note that all of these tools have been applied, of course, in quantum information theory and condensed matter theory and so on, in a very general way, because these are just generic tools you use to understand generic quantum systems. And so this is all inspired by this central dogma that black holes essentially behave like generic quantum systems. And so we should be able to use all of these tools and find that the behavior of black holes is consistent with all of these expectations, like the ETH, for example. So that's one set of ideas. The other set of ideas is another thing that I tried to emphasize before, which was the gravitational path integral. So in recent years, there's been a resurgence in applying the gravitational path integral to understand ADS-CFT. And in particular, this has been led by trying to look at lower dimensional models, like 2D models, like in particular, JT gravity has been one of these theories which has been used a lot. And the nice thing about it is that the gravitational path integral, we have a lot more control over the gravitational path integral as compared to in higher dimensions. So that has helped with understanding a lot of these things, and that in particular has led us to have some understanding of microstate counting, scrambling physics, and wormhole effects in gravity. So these sort of two themes are bridged together by what I tried to emphasize here, which was random tensor networks. And in particular, my work with Akers made clear this dictionary between random tensor network calculations and gravitational calculations in the gravitational path integral via what are called fixed area gravitational states. So there's some one-to-one correspondence between calculations that are done on the random tensor network and calculations that are done in the gravitational path integral, as long as you think about these fixed area states. These fixed area states are roughly like a basis for gravitational states, like the position eigenstates, for example, in quantum mechanics. And they have this nice feature where for example, the entropy calculation becomes much simpler when you do it in these states. So that's sort of the unifying theme. Once you have this translation, it upgrades some of the qualitative ideas that I tried to mention before, which in the sense in which tensor networks are toy models for ADS-CFT, to a sort of more quantitative connection, where you can really compute things in the random tensor network and translate it via this dictionary to the gravitational path integral and get results for gravity. So this has been an engine where we can generate new results for gravity using this. And I'll try to emphasize some of those now. Okay. All right. Okay. So one of the highlights, for example, of this sort of thinking is our understanding of entanglement phase transitions. So the Ryu-Takenagi formula, of course, tells you that you look for the minimal surface that's homologous to the boundary region you care about. Now, in a 2D CFT, if we take two intervals, then we can change the size of the interval, and there are two candidate surfaces, the green surface and the orange surface. And depending on how big the region is, there's a phase transition from one of these surfaces to the other surface. The way the random tensor network calculation goes here is you basically try to do the replica trick to compute the Renyi entropy. And the idea is essentially like what you would do in a conformal field theory. You apply twist operators on capital R and trace out its complement. And then what the random tensor network calculation effectively amounts to is looking for the ground state of an Ising-like model, where the degrees of freedom that live on the vertices are a choice of permutation. So instead of a spin, it's basically a permutation on n objects, where n is basically the Renyi entropy we're trying to compute. So different choices of this permutation in the center give you different phases. It can give you either the green surface or the orange surface, and when you're near a phase transition, there's a whole class of permutations that contribute, which basically smooths out this phase transition and gives you a smooth answer for the entanglement entropy. Now, this calculation, as I said, you can translate it to the gravitational path integral, and a particular example. Sorry, was there a question? Oh, okay.
No.
Yeah. And a particular example of this is the page curve of black hole evaporation. So page curve of black hole evaporation is just another special case of such an entanglement phase transition, where you have two candidate Ryu-Takenagi surfaces, and there's a transition depending on some change in parameters. What really happens when that happens is there's a change in topology of the dominant saddle, which dominates in the gravitational path integral. And in the random tensor network, there's a corresponding change in the ground state of this calculation that we're doing to compute the Renyi entropy. And so using this, we've understood entanglement phase transitions in quite a universal way, including corrections to the peak of the page curve and so on. So this is just one example where these sort of ideas have helped. Now, so some of my work has also involved trying to understand entanglement in the context of ADS-CFT. And as I told you before, the Ryu-Takenagi formula tells us that the entanglement entropy is given by the area of some surface in gravity. But the entanglement entropy is only a good entanglement measure when you're trying to measure the entanglement in a bipartite pure state. So if you have a pure state, then all correlation is basically entanglement, and the entanglement entropy is a good measure of it. But when you have a mixed state, then you need something else to measure the entanglement as opposed to classical correlation that can exist between two parties which are in a mixed state. So one such quantity, which is relatively easy to compute, is what's called the entanglement negativity. So the entanglement negativity is defined as follows. You start with density matrix on AB, row AB, and you perform a partial transpose. So you flip all the bras to kets on the B subsystem, and you keep it the same on the A subsystem. When you do this, this is no more a density matrix. It may not have positive eigenvalues. And the number of negative eigenvalues happens to be a good measure of the amount of entanglement between these two systems. So calculationally, this is like relatively close to the entanglement entropy calculation. The only difference is this extra partial transpose that exists on system B. And this is basically the simplest generalization you can imagine of the entanglement Renyi entropy calculation. Now, in the context of ADS-CFT, the Ryu-Takenagi formula was understood a really long time back. Even a derivation of it using the gravitational path integral was basically done in 2013 by Lefkowitz and Maldacena. And around that time, people also tried to understand the entanglement negativity. But the holographic dual of the entanglement negativity was very poorly understood for more than a decade. And Ryu of Ryu-Takenagi fame had previously proposed the entanglement wedge cross section, which is basically the surface that divides the entanglement wedge of A and B into two parts, as the bulk dual of this negativity. But by doing this random tensor network calculation, we were inspired to find a new solution. And this new solution actually breaks replica symmetry, unlike the situation with entanglement entropy, where the main assumption that goes into that derivation is replica symmetry. It so happens that in the random tensor network calculation, there are analogous configurations which look like this entanglement wedge cross section as seen on top, but there exist configurations in the random tensor network which are replica symmetry breaking permutations, which can split this domain, and then once you relax the domain walls, you get a configuration like the one shown below, which is actually the dominant configuration. So the naive replica symmetric configuration actually subleading to the replica symmetry breaking configuration. So this random tensor network calculation inspired us to look for similar things in gravity. And we came up with a new holographic proposal inspired by this in these papers. But the path was not so straightforward. Firstly, we had to argue in gravity why replica symmetry should be broken just like it was in the random tensor network. And the way we did this was by relating the entanglement negativity to a half Renyi entropy in what's called the double state. So the double state is basically like the thermofield double state, where you start with a density matrix and just flip all bras to kets and think of that as a new state. This was motivated from some previous work I did on another such quantity called the reflected entropy. And nevertheless, once you have this, this is actually sufficient to show that replica symmetry should be broken. But the issue was that Renyi entropies for n less than 1 had been poorly understood so far. Lefkowitz and Maldacena had made a proposal for what it should be, but we had done a calculation in JT-gravity where we have more control over the gravitational path integral, so we don't need to just do a saddle point approximation. We can actually resum many configurations and see what the more correct, more accurate answer is. And we found that for n less than 1, the Renyi entropies didn't match the Lefkowitz-Maldacena proposal. So we came up with a new proposal based on these ideas of fixed area states, which fixed these issues and matched these calculations even in JT-gravity. So with that, then we could finally translate all of these results to the gravitational path integral, and we found a very simple answer, and the answer looks almost exactly like the random tensor network answer, which is on top. It's basically very similar, except that you have conical defects sitting on these relevant surfaces. So the ones labeled 3 pi have an opening angle of 3 pi, and the ones labeled pi have an opening angle of pi. So these are just some extra conical defect angles that you're adding to the gravitational solution that you started with. But other than that, other than the back reaction caused by those conical defects, the answer essentially looks like this replica symmetry breaking answer in the random tensor network. So that sort of gives a complete picture for this new quantity, which we were missing for almost a decade and was entirely inspired by these random tensor network calculations.
Actually, Pratik, could you give us a sort of an example of the kind of calculations you do in the random tensor network that inspired these things?
Yeah, so let me explain this calculation. So the way the random tensor network calculation goes is you're trying to compute some replica trick, right? So there was this quantity that we wanted to compute. So let's say this E2k. It's basically trying to compute the 2kth moment of the rho AB transpose. Now, the way you do that is you impose boundary conditions so that you're cyclically gluing region A like you would in the Renyi entropy. You're tracing out region C because you're tracing out to get the density matrix for rho AB. And you're doing a cyclic permutation, but with a transpose. So that makes it an anti-cyclic permutation on B. So that sets boundary conditions for the tensor network. And then in all the vertices of the tensor network, you're putting in, you're looking at all configurations which have a permutation sitting on each of these vertices. So it's like an Ising model where you're allowing all of these different configurations, and you're basically in this large bond dimension limit looking for the ground state of that given these boundary conditions. So a simple configuration you can imagine, which would have been the ground state, is the top configuration, where I just extend the boundary conditions on the boundary into the bulk and just find all the energy cost. So there's an energy cost, just like the Ising model, there's an energy cost for two different permutations which are connected by an edge. So if there's an edge, then there's an energy cost associated with, say, having X on one end and the identity on the other end.
So sorry, but is this there is some construction going on? I'm sorry about that, but is this work done numerically or analytically?
No, this is an analytic solution. So you can basically in this large bond dimension limit, you're literally looking for the ground state of this model, and you can analytically find it. So the configuration that's below is an analytic solution to the entanglement negativity of the random tensor network, and it's given by this picture, which you can interpret as min cuts of a certain type in the random tensor network.
Okay.
Yeah. You can, I mean, numerics actually helps for many of these things because sometimes you need to guess what the answer should be and so on, and like have consistency checks and so on. So numerics helps, but you can do all of this analytically. So this is something that you can just prove analytically. Sorry, so just going back to what I was saying, you're looking for this ground state, and you can find a particular permutation which gives you this best ground state for this answer. So that's the sort of calculation that's being done here.
Okay, but if I take this random tensor network and compute like excited states, what do they correspond to in the
excited states in this
excitations?
like model?
Yeah. If I do that, what does it
Yeah.
mean in the
So what we're doing here is we're looking at the large bond dimension limit. So the reason we're looking for the ground state, so the thing that's controlling the temperature is this bond dimension. So if you have bond dimension going to infinity, that's like taking beta to infinity and like looking for the ground state. If you're at finite bond dimension, then there's finite corrections that come in from these bond dimensions, which would be like the contributions from the excited states in this Ising model. There is no, I mean, those you can, so those would come from, say, a different configuration where, let's say, the domain domain configuration that's shown below is like slightly different. Those would correspond to like different configurations in gravity where you're not at the leading saddle point, but it's like let's say, for example, for the entropy, it's like replicating around not the minimal surface, which wouldn't be the RT surface. Those sort of configurations, which are subleading in the gravitational path integral, are like they're non-perturbatively subleading in the gravitational path integral, are like the contributions from the excited states in this model.
Okay, thanks.
Is there any other question?
Yeah, I have one thing. So can you show me the figure where you wrote pi, 3 pi?
Yes. Yes.
So can you explain that? I couldn't
Yeah.
follow.
Good. So what we did essentially, so here's what, firstly, like in the random tensor network calculation, like we just found what the ground state is, and that's given by the upper picture. So that there, we're good. Now, what you can try to do is essentially use random tensor networks. So there's this relation between these random tensor networks and fixed area states. So you can think of these fixed area states as some sort of basis for general gravitational states. There's a way to compute the wave function of.
So before that, like this fixed area state, can you give me some intuition? What is that state?
Yeah. So okay. So let me say this. So the way we do the path integral. So imagine we were looking for the Hartle-Hawking wave function. So what do we mean by the Hartle-Hawking wave function? We have some boundary conditions at infinity, and then we specify some metric. So let's say we specify metric h, and then we fill that in with some saddle point, which gives you psi of h, which is the wave function as a function of h. So now just think of the state which has psi of h being a delta function, or like or very close to a delta function in h. So it's as if you fix the induced metric exactly, and then there's like large fluctuations in the conjugate variable, which is the extrinsic curvature. That would be like a fixed geometry state. And all we're doing is taking some state psi, like say the thermofield double or the vacuum of the CFT, and just writing it in this basis of fixed h, essentially.
Fixed h.
Yeah. So fixed area was like the preliminary thing, but like you can basically fix the whole geometry, the induced geometry on that slice.
I see. Okay.
So
No,
you
this,
use
this
sorry.
3 pi. Can you?
Yeah. So you use that fixed geometry basis. The fixed geometry basis, you can like directly translate the gravity calculations in that fixed geometry basis to this random tensor network calculation. So then you know the answer in a fixed geometry, like in a particular geometry. And then all we're doing is restoring the fact that really the state was a superposition over all of these different geometries, and then picking the saddle point, like picking the dominant term from that sum, essentially. That amounts, like when you translate that to gravity, that amounts to picking a particular conical defect angle. I'm sorry, I'm skipping a lot of the details here, but yeah.
So the confusion for me is like this final result that you get, will that be a saddle of, will that be a geometry that contributes to gravitational path integral?
Yes, it is. So in the original, so the original state that you prepared has some boundary conditions, and when you fill it in, this is one of the things that contributes to that, like even the norm of the state, but it's a sub-leading contribution to the norm of the state. When you compute the negativity, it's similar to the Renyi entropy. Like when you compute the Renyi entropy, as n goes to 1, you just find some area in the original geometry that you have, but at any other n, it's like a different geometry, like there's some back reaction and you have some different geometry which has a conical defect, which also contributes to the norm, but in a very subleading way. But when you compute the Renyi entropy, that's the dominant saddle. So it's similar to that, where this is like a subleading contribution to the norm, but it's the leading contribution to the entanglement negativity.
I see. So there, the other computation, the Renyi computation for finite n, you think as if there is some object sitting, right? So,
Yes.
Here something analogous is
Yes, so the way people often say this is there's a cosmic brain sitting at that location, which is sourcing this conical defect. So you can basically tune the tension to give you these opening angles, and that's another way of thinking about it.
I see. Okay, okay.
So you can
Thank you.
think that the twist operators that were acted on the boundary sort of source that brain, basically.
Okay.
I couldn't really understand. I thought you were trying to describe what is the bulk dual for negativity, right?
Yes.
So from this figure, I
Yes.
don't really cannot see what you're saying is the bulk dual. Can you say?
Yeah, it's not very straightforward to say. It's basically like, so there's some action of this configuration, and the negativity ends up being the difference of action of this configuration versus the original n equals 1 configuration.
I see. So you compute action for this versus for n equals to 1.
Yeah,
in this figure, what n corresponds to this? You're saying there's some n corresponding to this figure?
Oh, this is specifically for the negativity. So the negativity was like the k goes to half limit of this calculation.
Okay.
So, I mean, you can also compute it at all k, but the one we were interested in, like, because it's an entanglement monotone, is the negativity. So that's like in the k goes to half limit. And in the k goes to half limit, the answer looks like that.
I see. So difference of actions between two geometries.
Yes, that's also the same as the Renyi entropy. Even in the Renyi entropy, like really it's like you find this configuration with this cosmic brain and you compute the difference of action between that and the original geometry. So it's similar to that.
Okay.
Okay, so that's sort of one of the, so this is meant as a way to explain how random tensor networks have taught us new things about gravity that we didn't know otherwise. So this is one such example. So let me give you another such work, which is more recent, which is in trying to understand black hole microstates at low temperatures. So as I said before, JT gravity is this two-dimensional theory which has a large number of black hole microstates, order e to the s0, where s0 is a large parameter, and it's related to higher dimensional black holes which are near extremality. So in this theory, it's been well understood that the gravitational path integral is very much under control, and calculations in the gravitational path integral are in one-to-one correspondence with random matrix theory calculations, which you should interpret as somehow the boundary theory. So this is some sort of generalization of ADS-CFT, where instead of having a particular CFT dual to a gravity theory, you have a whole average over many theories, which is reproducing the calculations that the gravitational path integral computes. So in this theory, the partition function can be computed exactly, and it looks as follows. There's an e to the s0 over beta to the 3/2. And when you process this and try to compute the entropy, just the thermal entropy, you find the following. So it's something that's positive for basically order 1 temperatures. But when you make the temperature really small, so here we're plotting beta, and at beta of order e to the 2/3 s0, which is like temperatures of order e to the minus 2/3 s0, so exponentially small temperatures, the entropy goes negative. So if you just take this partition function, compute the entropy, you find that it goes negative. So this is a puzzle, some sort of version of an information-like paradox where the entropy is going negative, whereas we know it should be positive. So the way we try to understand this is by realizing that in this particular example, the gravitational path integral is computing things that are dual to averages over a random matrix theory. So there's many different ways in which you can take the average. And one of the ways, which is the simplest way in which people usually compute entropies, is what's called the annealed entropy. So the annealed entropy is where you compute things that are obtained from log of the partition function, where the partition function has been averaged. That's a simple thing because the partition function average is just a one boundary quantity which you can compute, similar to the pictures I showed before about the gravitational path integral. This is simple to compute, but it can be negative in general. The true thing that one wants to compute is the quenched entropy, which is where you average the log of the partition function and then try to compute the entropy. This is difficult to compute, but we know that it's positive because it's truly the average entropy of all of these systems. So the reason it's hard to compute is because computing log of the partition function is challenging. The way it's usually done is by a replica trick where you compute z to the power of m, where m is an integer, compute this for all m, and then analytically continue m to 0. This m going to 0 limit is a very subtle limit, and in fact we've shown that it doesn't commute with this low temperature limit, and so it's really difficult to compute the quenched entropy in gravity. Now, since there was this negativity paradox, what we were interested in was to try to show that the quenched entropy nevertheless stays positive. And to do this, we invented this other intermediate quantity, which we call the semi-quenched entropy, with its Renyi versions. The semi-quenched entropy is defined as follows. So we try to compute the Renyi entropy, but we average the numerator and denominator separately. This is a quantity which you can show is positive. And moreover, if you show that it's positive for all beta, it's enough to prove that the quenched entropy itself is positive for all beta. So we use this intermediate quantity as a sort of tool to try to prove that the quenched entropy nevertheless stays positive, even if the calculation for the quenched entropy is difficult.
Hey, Pratik, is it also following additivity?
I think it should follow. You mean just like if I take tensor product of two systems, the entropy adds?
The entropy adds up. It's
I
extensive quantities.
think it should, because the partition function.
Because you've taken the average within the log, right?
Yes. So the partition function will just multiply, right? Like you're just imagining like tensor product of these two things, right? Like not entangled states or something.
Yeah, means that should be the property of entropy. If we define it in that, if we want to define this quantity as entropy, then it should follow that.
Yes, and the partition function will multiply, but there can be correlations. So I'm a little worried about that actually. I mean, the problem here is that we're not looking at a single theory. In a single theory, of course, as you said, like there will be this additivity property. But because we're averaging over theories, if you do the average in a correlated way between these two systems, then there can be an issue with additivity. If you average them separately so that there's no correlation in the averages, then it will be additive.
Mm-hmm.
Like basically because the partition functions will factorize. So for that reason.
And how do you see which is, so what did you do in your theory here? So
here we
sorry, go ahead.
Yeah, here we computed these separately, like the average of z of n beta and the average of z of beta to the n. Here it was just one system that we had, and for that one system, the average is taken in a correlated way. Like there's basically the same Hamiltonian for all of these systems, for that system. And so the averages, they do have correlations and so on. So these averages don't satisfy some simple additivity property. Like z of beta to the n average is not the same as z of beta average to the n, for example.
Okay. Yep.
Okay. So, by the way, how are we on time? I just wanted to.
You have 30 more minutes.
Okay. So I can certainly say this. Okay. So the way we compute this is relatively simple. So now the reason is you don't need this analytic continuation to get the log. You can just compute this thing. So for example, for n equals 2, the numerator is z of 2 beta averaged. And the way you compute this using the gravitational path integral is you have one boundary of length 2 beta, and you fill that in with some configuration. So in 2 dimensions, you just fill it in with a disk at leading order. And then there's sub-leading corrections, which are exponentially suppressed in S naught, which are like the higher genus version of the disk and so on. Now, in this limit where we take beta to be also really large, so that the temperature is really small, it turns out that all of these different higher genus corrections are just as important as the leading disk term. And so what you really need to do is resum this whole series. In the limit where you scale beta to infinity and e to the s naught to infinity in a double scaling limit where you take beta to be of order e to the 2 s naught over 3, which is where we saw this negativity arise. This is something that's actually understood. So this is something that's called the Airy limit of JT gravity, which is where you're basically taking the random matrix theory, zooming in to the edge of the theory, and there's a universal behavior that's dictated by the Airy matrix model. So this is understood, and we can actually do this sum analytically and find what the total partition function is in this limit where the annealed entropy is actually going negative. We can also compute z of beta squared, which is the denominator here. And the way to calculate z of beta squared is you have two circles of length beta. And other than the disconnected geometries that contribute to it, there's connected geometries because of the correlations between these two Hamiltonians. And so the first connecting geometry is the cylinder, and then there's higher genus versions of the cylinder and so on. And again, all of these become equally important in this limit, in this double scaling limit. So you really need to do a resummation over all genus to get a sensible answer. So what we did was we did this, and when you do that, you find the following. So you find that the blue curve, which is the annealed entropy, goes negative around temperatures which are e to the minus 2s naught over 3. But the semi-quenched entropy turns around, it gets important contributions from these connected geometries, and it turns up and basically goes to 0. So it stays positive for all temperatures, as expected, as you wanted. And since you've proved that the semi-quenched entropy stays positive for all beta, it's also true that the quenched entropy is positive. So this was basically how we were trying to understand black hole microstates at these exponentially small temperatures. Okay. There's a similar sort of version of this paradox, which is a slightly generalized version, where instead of looking at the thermal entropy, you look at an entanglement entropy. And the way you think about this is, imagine you have the thermofield double state, but in the Euclidean past, you add matter insertions, which are heavy. These matter insertions basically make a longer wormhole. So the colored shells in between are basically some matter insertions, which split the horizons and make the wormhole a little bit longer. And there's all of these pink dots are basically extremal surfaces in between these matter insertions. One model for this is basically having a tensor network. So again, a random tensor network where these random tensors essentially are the insertion of these heavy matter operators. And the legs connecting them represent the extremal surfaces that are separated by these matter insertions. When you try to compute the entanglement entropy of this, the entropy goes down as you add more and more matter to make the wormhole longer. And when there's exponentially long wormhole, when there's exponentially many matter insertions, you find again this paradox that the entropy goes negative. The entanglement entropy this time goes negative. Again, going through with this random tensor network calculation and translating that to gravity, you basically find that there's these similar higher genus-like wormhole configurations that I showed you on the previous slide, which need to get resummed, and they get resummed to give you a positive answer again. So again, we find that the semi-quenched entropy is positive, which also again means that the quenched entanglement entropy is positive. So that's another paradox in gravity, which we basically resolved by trying to understand a simple toy model for it, which was this random tensor network. Okay, so let me try to very quickly summarize some future things that I'm trying to think about right now, which is that even despite all of this progress in trying to understand black holes, the black hole interior is still very poorly understood. And in order to really highlight this, Stefano Antonini and I wrote a paper trying to give this illustrative example, which is a very simple ambiguity involving closed universes in ADS-CFT. And the puzzle is basically the following. The gravitational path integral has some solutions which involve the following configuration. It basically has two ADSs, which are these blue cylinders, which are entangled with this yellow closed universe. So there's some closed universe which is just completely disconnected from the ADSs, and it's entangled with an order 1 amount of entanglement that's connecting the closed universe to the ADSs. Now, this is a state in the CFT which has order 1 energy and order 1 entropy. These are states we usually think we understand. We can just generate them using the extrapolate dictionary. And so there's an alternate description for this particular CFT state, which is just given by the standard ADS CFT dictionary, which is the extrapolate dictionary, where there's two ADSs, they have some entanglement between them, and there's no closed universe at all. So in one description, you have a closed universe, whereas in the other description, you don't have a closed universe. And this is a puzzle that has gotten people interested. Various people have proposed various resolutions. I don't think there's any satisfactory resolution as of now, but motivated by some of these random tensor network pictures, we tried to model this using random tensor networks and try to argue that if something like the final state proposal of Horowitz and Maldacena is going on, then somehow both of these descriptions are dual to the same CFT state. So this is traditionally the way people think about ADS CFT is as an isomorphism between ADS states and CFT states. And here what we're trying to say is it's more like a non-isometric map where we have multiple ADS states getting mapped to the same CFT state. This is not unfamiliar. The same sort of physics also goes on in the Page curve in the black hole interior. But it's still a pretty radical thing because this is a regime where we thought we understood ADS CFT pretty well. So it somehow seems that in all of these proposals that have been made to try to resolve this puzzle, that some level of coarse-grained description is important. This is also something that showed up in the random tensor network where we were trying to match some randomness, some random calculation to what was showing up in the gravitational path integral. And so I think this is a very intriguing suggestion that somehow gravity only emerges as some sort of thermodynamic description of space-time. This slogan has been said at different times for different things, and I think this is a version of that, where somehow gravity only emerges under appropriate amounts of coarse graining. Okay, so I'm going to skip this and just give you a broad vision for what sort of work I'm trying to do. One of my key motivations with all of this work is to try to understand quantum gravity in our universe, right? So we'd like to understand our beautiful cosmology, and ADS CFT is useful, but it only goes so far because we only understand gravity in this box of with a negative cosmological constant. Now, the goal here has been to try to use bottom-up methods. So the key things I tried to emphasize were the gravitational path integral and these ideas from quantum information theory. These don't as heavily rely on ADS as compared to us having only top-down versions where we understand ADS. And so the hope is that lessons that we learn from here will be applicable more generally. Sorry, was there a question? Okay. So the hope is that we can use some of these lessons to apply more generally and hopefully try to understand our cosmology. As I pointed out, even in ADS CFT, we still don't understand the holographic dictionary well enough. And so we're still trying to make sense of that. And so we're far from this goal, but this is just some vision for the future. So one thing that I think is an important thing to do is somehow push for more realistic tensor network models. As all of you complained, there's aspects that are not here, like diffeomorphism invariance, time dependence, and so on. And one direction I see here is there's this thing called the double scaled SYK model, which has a nice interpolation between the JT gravity description and a random tensor network like description. And trying to understand this better may help us understand this more concrete tensor network description of gravity. And in particular, the missing thing that's very poorly understood is time dependence. And so this is something that is an open problem that I'd like to attack. And again, as I emphasized, it seems that randomness plays an important role in the emergence of the space-time description. Random tensor networks are a good example of this. Recent work on large N von Neumann algebras is another example of this. And resolutions to the puzzle that I posed here with the closed universe have all seemed to require some sort of this randomness. So I think it's very intriguing, and we'd like to understand better in what sense this coarse graining is needed for an emergence of a space-time description. Okay, so with that, I'd like to thank you.
Thank you. Any questions?
Hi, Pratik. So when you mention these calculations in the tensor network models,
Yes.
and then do a gravity dual of it, so all these are done in 2 dimensions, or you can generalize it to higher dimensions?
No, so the random tensor network gravitational path integral connection is independent of dimension. You can do it in any
Okay.
dimension you like. It's just a formal thing with the gravitational path integral. The thing about higher dimensions is that the gravitational path integral itself is a little poorly understood. So in 2 dimensions, you can do a lot of things more concretely because we have more control on the gravitational path integral itself. But the connection between configurations in the random tensor network and configurations in the gravitational path integral is independent of dimension. So like, for example, these dominant configurations that we find for the entanglement negativity and so on, you can translate those to higher dimensional gravitational solutions.
And your gravitational calculations that you're doing, these
Yeah.
are all semi-classical, right? Or you do
Yes.
like...
There were both kinds of calculations. So the entanglement negativity calculation was kind of semi-classical in that it's dominated by a particular configuration, and there's like small corrections to that. So you're sort of doing a saddle point approximation around that. But the second calculation that I talked about, which was in trying to understand the positivity of the entropy, was one where we really had to resum all of these geometries. So that is a very non-semi-classical calculation where you really need like this full resummation over all geometries and so on, and that's actually important.
But then you have to know all the basis states very well, so
Yes,
that
that's right.
you
That's
can
right, and that's
calculate the
why
path integral in an exact manner. Otherwise, it is a very difficult problem, I would say.
That's right, that's right. So that's why that calculation was limited to 2 dimensions, where we did it in basically JT gravity. In higher dimensions, you need much more control, and we don't have that right now.
Okay, so this tensor network model and gravity correspondence, this is like an means I'm not an expert here, but there's some kind of analog to this ADS-CFT correspondent that you're proposing?
Yeah, I mean, this is not my proposal as such. Like going back to 2009 or so, like Brian Swingle had come up with this idea that there was some sort of qualitative connection between how the ADS-CFT dictionary works and how these tensor networks work. And what I'm adding to this story is basically that people basically thought of this as a very qualitative connection, but there is the more quantitative connection to it if you think about these random tensor networks.
Actually, sorry, just to follow up on Sayantan, could you just give us an example of a concrete computation you can do in the random tensor network and how it translates to the gravity? Is it possible for you to show in finite time?
Okay, one example.
Sorry, Sayantan, yeah.
One example I talked about was this entanglement negativity, which is an example. I'll give you a simpler example. A simpler example is just the Renyi entropy. So if you imagine computing the Renyi entropy, the way that calculation goes is as follows. So the calculation looks like this. So you have some region R, and you're trying to compute the Renyi entropy of that. Now, in the random tensor network, what that amounts to, I mean, we can do this calculation, and amounts to basically picking out the min cut in this.
But what do you concretely do? I mean, since I'm not an expert at all, so I just want to understand what do you do? What do you take a Hamiltonian of particular kind?
No. So what's being done here is, so because you have these random tensors at each location, what we're doing is we're going to compute an average over these random tensors. So when we're integrating over these random tensors, that sort of simplifies the calculation to this Ising-like model that I was mentioning, which is where at each location you have a choice. So you have, say, n copies of this tensor network, and the boundaries of this tensor network are glued in a particular way, just like in ADS-CFT. Like when you're computing, say, trace row to the n, what you do is glue the boundary path integral in this cyclic fashion and then fill that in, right? So here in the random tensor network, what's happening is we take n copies of the tensor network, glue the boundaries appropriately, do the average over over these random tensors, and then what that amounts to is at each location in this geometry, in this discrete geometry, you're basically allowed to glue it to any of the other copies in whatever way you like, and that is basically specified by a permutation. So in the simplest thing that I can show you in this picture, we start with gluing the region R in some cyclic way, and the ground state will be such that this blue region is always glued cyclically. So there's a lot of tensors there, which are these discrete things that I've not drawn here. So here I've just drawn sort of a continuous picture. But you can imagine that in the blue region, there's like a lot of these little dots, which are these tensors. And all of those tensors are basically getting glued cyclically in the bulk, just like in ADS-CFT, where when you do the gravity calculation, so in the gravitational path integral calculation that derives the Ryu-Takayanagi formula, what ends up happening is the region that's green gets glued cyclically in the path integral, and the region that's outside it gets glued trivially. So the random tensor network sort of mocks up that aspect of the gravitational path integral. Now, since here what we're doing is fixing the geometry, all of Einstein's equations don't need to be solved, and so you're allowed a conical defect at this location. But then what you can do is think of this random tensor network as a basis, and think of a smooth state in gravity, which you can think of as a superposition over these random tensors, and that essentially gives you a smooth solution in gravity. So that's sort of the rough way in which this goes. Did that answer your question?
Not entirely, but it's fine. I think Saithan probably has follow-up. I just wanted to interrupt him briefly to ask you this question. Okay. Anyway, yeah, sorry. Yeah.
No, it's fine, Sujay. I didn't have any further questions. I was just asking. Yeah. You can continue.
There's just one clarification, I think, short clarification about, you mentioned about this closed universe ambiguity.
Yes.
Right? I was just wondering whether it is related to this monogamy of entanglement, because you seem to have two regions maximally entangled to one. And
yeah, so that's a good point. So what's happening really is in the semi-classical description, there is this tripartite entanglement. So in the first semi-classical description, there's bulk entanglement between ADS1 and closed universe, ADS2 and closed universe, and also ADS1 and ADS2, right? So there's all of this tripartite entanglement. But if you try to compute the boundary entropy, what will end up happening is that the closed universe, because it doesn't have a boundary, it can always be included as an island for one of the ADSs. So the one which has more entanglement with the closed universe will get included as an island as part of that. And what you'll find is that the entropy is perfectly consistent with the right picture. In the right picture, all you have is entanglement between ADS1 and ADS2, and the missing thing is the closed universe. But that can be compensated for by thinking of an island, which is this closed universe, which also has some entanglement with ADS2.
But you're talking about islands in thermal ADS, right? Not in...
Yes, that's right. So the new feature here is that there's no black hole interior. What's really happening is that so the way these solutions are formed is you add like a heavy operator in the Euclidean past. This heavy operator usually would have formed a black hole. But then what you do is you allow a large amount of Euclidean evolution to cool down the system, so that it effectively goes below the Hawking phase transition. So this is like a thermal ADS-like solution as seen from the exterior, but the matter has to go somewhere. And what happens is it basically goes into its own closed universe.
Okay.
Okay. So effectively you're below the Hawking phase transition, and that's why we have this thermal ADS-like picture on the right. But the Euclidean solution that prepares this state does have this closed universe, like on the symmetric slice.
Pratik, I had a very naive question. So suppose we do gauge theories. So then all the universal features like the eigenvalue levels, spacing separations of the Hamiltonian and all, these are related to random matrix theory.
Yes.
So now you have these tensor networks which have some universal properties corresponding to strongly coupled gauge theories.
Yes.
Now, what is the statement? Is some universal features of it is related to some universal features in the gravity side, or is it that tensor network models can predict even bulk properties in gravity, or only the universal properties in the gravity?
Yeah, I would expect that it can only predict universal properties for the reason that, I mean, in the sense that because we're approximating things by these random tensors, we're not like necessarily picking out the specific choice of tensor that, is corresponding to, say, this particular gauge theory. It won't, I mean, it's coarse grained enough that it won't necessarily know the details. If we were powerful enough to prepare the specific tensor network that corresponds to a specific theory, then you could compute the exact details and it would know about the bulk. But the level at which the calculations I have done are there, it's I think you've coarse grained away that information essentially. Like imagine you had some parameter on the boundary, like say the Tuft coupling or something. Different choice of Tuft coupling will correspond to like slightly different tensors. But since we're averaging over all tensors, you've sort of lost that information.
Yeah, but anyway, it will be interesting for the universal properties in real-time dynamics also. Yeah.
Yeah, like for example, like the entropies, satisfy like these are self-averaging quantities. Like no matter what choice you would have picked of these different parameters, you would basically get similar entropies, and the random tensor network knows that.
And can you also calculate OTOCs and all of these things in the gravity side?
You could, but again, that's like because it relies on time dependence. We don't really understand the description very well. There are versions of this, like instead of having random tensor networks, you draw like random unitary circuits. And the random unitary circuit calculation basically reproduces exactly what you expect from the OTOC. So it's like a version of this, but I won't say that the picture is very clear. Like there's no nice bulk picture.
Okay. Yeah. Thanks a lot. Yeah.
Thanks.
I have one thing. So in random network, is there any way to introduce something like a horizon? Like if I want to study.
Yes, you can. So what ends up happening is, so imagine this tensor network where, why can't I use? Okay, so imagine I just remove some of the tensors in the middle, and just like have some open legs in the interior as well. That's basically how people modeled black holes using this tensor network. It's essentially some region in the middle where you've eliminated all the bulk information and it's sort of like a blob now. You don't know about it. So in many of these tensor network discussions, the way people discuss it is there's some code subspace, which is there's some set of states on the boundary which corresponds to, so here you have these yellow dots that I've represented. You should think of the yellow dots as sort of, if you're projecting some bulk state there, so you have some QFT state, you project a QFT state onto those legs and it spits out a boundary state, which is the CFT state. Now there's some subspace of states in the CFT which has this nice description, which is just like vacuum ADS plus like some perturbations which are QFT. But if you put some crazy QFT state there, that's basically going to form a black hole. And so that's basically like going outside the code subspace that this tensor network has defined. So this a way to model it is by basically destroying some part of the network and allowing yourself to access like a larger set of states which aren't of the form of this exact graph. It like breaks some of that structure.
I see. Okay. Any more questions? Anybody in the online? Okay, if you don't have any more questions, let's thank Prateek.
Thank you so much.